Hello everyone. We were discussing the chapter Gaseous Laws and Thermodynamics, and we have learned in the previous lecture the zeroth law of thermodynamics, and we have learned about the notion of temperature and the heat energy. We discussed what is the work done by a gas, and we did one process as well, that is the expansion of a gas under constant pressure. And we learned what is the importance of the PV curve in the thermodynamical processes. Now we will begin with the first law of thermodynamics, as well as we will discuss some concepts like internal energy and various others. So let's begin. So the first concept we are learning today is the internal energy. Internal energy of a gas. So internal energy is basically denoted by U. Of a system is nothing but total of all kinds of energy possessed by a gas or the other particles that comprise a system, basically. Okay. So basically we are dealing with the internal energy is nothing but a combined term for all the different type of energies that our energy molecules could have, like the rotational energy, like the vibrational energy, like the electrostatical energy. So it is basically a combined form of all these internal types of energies that are not distributed by it is not represented in the external forms by the gas. So this is a combined term for the internal energy. Okay. So the combined form for all these internal factors is basically the internal energy of the gas. Okay. So change is basically change in internal energy. So this is very important point over here. The change in internal energy of a gas is dependent only on the difference in the temperature between the initial and the final state. Okay, so we mean to say that the internal energy change, that is delta U for a process, is nothing but some constant into delta T. So the internal energy of a system can be very easily defined in terms of a temperature, and this, as we can see, that it depends only on the temperature difference, not on the process where you went through. So basically we can define the internal energy at a given state. So if the state is if the gas is at a state P, V and T, we can very easily define the U for it, the internal energy for it. And if somehow it reached another state, that is P1, V1, T1, so the internal energy would be, say, let's suppose U1. So we mean to say that U1 minus U is nothing but sometimes constant into T1 minus T. It has no relevance to the pressure or the volume. It is dependent only on the change in the temperature. Okay. So the internal energies or the various contributing energies are so mixed up or scaled in such a manner that it is dependent only on the temperature of the gas. Okay. So the next concept we want to learn is basically the first law of thermodynamics. This is another important law which is basically the fundamental of basically all conversions. It says that if some heat is supplied to the system, capable of doing some work, the quantity of heat absorbed heat absorbed by the system is nothing but equal to the total external work done by the system, total external work done by the system and the change in the internal energy. Okay. So basically this is a restatement of the law of energy conservation. Law of energy conservation. It says that if you supplied some heat given to the system, is basically divided into two parts. Work done by the system and the change in the internal energy. So basically we are saying that whatever heat you supplied from outside, it is either exhibited in the form of work done because it is the external representation of energy by a gas or a system, and otherwise it can go to the internal energy. That is the internal contribution to the change in the state of the gas, or basically the change in the state of the molecules. So we are saying that it is just a law of energy conservation. It says that neither energy can be created nor it can be destroyed. So that's we are saying that whatever amount of heat energy you put into, it is utilized in two forms. Either it goes to the work done by the system, or it goes to the internal energy of the system. Okay. Now, while considering, as we knew that the symbol for heat is basically Q. So the heat given is basically delta Q. And the work done is, so change in the internal energy is delta U is equal to, plus work done by the gas. So you must be careful over here. We define delta Q, delta U, but not delta W. This is because delta Q is a state function. State function is nothing but a property that can be defined just by the virtue of volume, temperature and pressure of the gas. Okay. So these are the properties which hold just by the given properties. That a gas is in this state, you can very easily define the heat of that system. Okay. Similarly, the internal energy can be defined precisely by knowing the volume, temperature and pressure of the gas. But work done, there is no work attribute defined to a gas in a particular state. This happens, work is only done by a gas when it goes through a process. Okay. So basically we can define the change in the internal energy as delta U, that is the U final minus U initial, as well as the heat as heat final minus heat initial. But work is defined for a process only. You can't define as work final minus work initial, because at the final state there is no work at present with the gas. It was done by the gas throughout that process. Okay. So this is basically the first thermodynamical law. First law of thermodynamics. Delta Q is equal to delta U plus W. Okay. While applying this equation, you have to be careful, because there are some sign conventions which you need to take care while doing this, while using this equation. Okay. So there are various sign conventions. So the first sign convention that we must be familiar with is work done by the system is taken to be positive. Work done on the system is taken to be negative. Okay. So this is the first sign convention. whatever the work is done by the system or the gas is taken to be positive, and whatever the work the external bodies or let's say a human does on the piston or the system, it's basically taken as negative. Okay. The second sign convention says that heat gained by the system is taken as positive, and heat lost by the system is taken as negative. We mean to say that if we supply 20 joules of heat energy into the system, that is, let's suppose you transferred some heat energy into the system, that we will take as plus 20, and somehow the outside environment is, let's suppose, cooler than the present system, so the heat would flow out of the system, then we will take in this equation the heat as minus 20 joules. Okay. The third sign convention says that increase in the internal energy is taken as positive, and decrease in internal energy is taken as negative. That is to say that if a gas gets its temperature increases, we can say it in this form as well, because the heat energy is directly proportional to, or the internal energy is directly proportional to the temperature. Because, so if we are increasing the internal energy, that means we are increasing the temperature as well. So from somehow we try to increase the temperature of the gas, then we take it is as positive gain in the internal energy. And if the temperature of the gas is falling, we take it as the negative or the decrease in the internal energy. Okay. So these were the three sign conventions related to the each and every term of the equation that defines the first law of thermodynamics. Okay. So till now in this lecture we have learned what is basically meant by the internal energy and what is the first law of thermodynamics, that is an instantiation of the law of energy conservation, and we defined the sign conventions that are to be followed when using the equation. Okay. Now we are moving on to an important concept known as the specific heat of a gas. Okay. Basically, specific heat of any substance is defined as the heat or say amount of heat required to raise the temperature of unit mass of a substance through 1 Kelvin. So this is for any general substance. We are dealing the specific heat of that substance is defined as the amount of heat energy that is required to be supplied to the substance in order to move its temperature through 1 Kelvin. Okay. So there is one important thing over here is there could be infinite specific heats of a gas or any other substance. Okay. So ideally a gas has infinitely many specific heats. Okay. Why is it so? Because the temperature of the gas can be raised through 1 Kelvin in different situations, in different conditions. We can raise this temperature under constant volume as well, under constant pressure, or we can say that the pressure varies under, say, a quadratic equation. We can have any condition under which we are trying to find the energy required to raise the temperature of the gas by 1 Kelvin. Okay, so ideally the gas has infinitely many specific heats, but in specific we will be dealing with just two types of specific heats of a gas, that is specific heat under constant volume that we basically write it as CV. C is the symbol for specific heat, and V is the parameter we are keeping constant. Okay. Similarly, there is a specific heat of a gas under constant pressure, that is Cp. Okay. So basically Cv is nothing but, it is defined as the amount of energy, amount of heat energy defined as amount of heat energy required to raise the temperature of 1 mole of a gas, because that is the unit mass for a gaseous substance. Okay, mole of the gas by 1 Kelvin. So Cv is different for each and every gas, because some gases might require some less amount of energy to raise 1 degree Kelvin temperature, other might require more amount of energy in order to raise this 1 degree temperature. Okay, so the heat, so basically we can say that for one molecule, so for a gas, if you are raising by 1 degree temperature, the temperature by 1 degree Kelvin, we can say that delta Q is Cv, and there is for 1 mole. So by following the unitary method, we can say that if you are changing the temperature for n moles of a gas by just 1 degree Celsius, we can say that it is NCV. And if further applying the unitary method, we can say that if you are changing the temperature of the gas by several degrees, we can say that delta Q is equal to NCV delta T. Okay. So this is basically the change in, or the heat supplied in order to change the temperature of n moles of a gas under constant volume by temperature delta T. Okay. Similarly, Cp is the amount of heat supplied in order to change the temperature of 1 mole of a gas by 1 Kelvin under constant pressure. Okay. So basically, following the similar procedure, we can say that delta Q is nothing but Cp. Similarly, if you are changing the temperature of n moles of a gas, that is NCP. And similarly, if you are changing it through T degree Celsius, we can say that and delta Q is equal to NCP delta T. Okay. So one thing you must understand just by the notion itself, that Cp would be greater than Cv. Now how can we say that? This is because, as we learned the first law of thermodynamics, which says that delta Q is nothing but delta U plus work. Correct? This is what we knew. In the first case, we are saying that there is no change in the volume. But as we learned that the work done by a gas is nothing but dW is equal to P into dV, and we are saying that the volume is not at all changing, that is under constant volume. So we can say that the work done by the gas is zero. So all the energy we are providing is just going into changing the internal energy, and internal energy is the direct measure for temperature. So delta U is proportional to delta T. So we can say that giving it less amount of energy changes the volume, changes the internal energy by the same amount. In the case of constant volume, it would change it by the less amount in the case of constant pressure. So that means we would need to supply more energy in order to change the temperature of the gas by the same amount. So this concludes that Cp is greater than Cv. Okay. So there is a ratio basically in which is known as gamma, which is nothing but the ratio of the Cp upon Cv. So this is the important quantity for the gas, for any particular gas. Okay. So basically we are saying that so ideally there till now we have learned that there are two basic specific heats which we are interested in. Otherwise there are infinitely many specific heats of a gas. The two we are interested in is Cp and Cv, that is under constant pressure and under constant volume. So the important quantity among them is gamma, and we have gamma always greater than 1 because Cp is always greater than Cv. Okay. So now let's try and understand the relation between these specific heats. One relation is that Cp is always greater than Cv. Okay. So first of all, for constant pressure, constant volume, let's suppose. Okay. So work, as we knew that it is equals to 0 because dW is nothing but P into dV and the volume is not at all changing. So we can say that the work done by the gas is nothing but 0. Okay. Now apply the first law of thermodynamics that says that delta Q is equal to delta U plus W. So in this case, delta Q is nothing but delta U. Okay. So as we knew that the energy supplied is nothing but N into Cv into delta T, that we learned just now by the unitary method, that to raise the temperature of 1 mole of a gas, we need through 1 degree Kelvin, we knew the energy required is Cv. So we multiplied with N into delta T to get the total energy supplied from the outside in order to change the temperature by delta T. So we get that delta U is nothing but NCV delta T. But one thing is very, very important over here is that U is a state function, as we discussed a few minutes ago. State function. So the state function has the property that the net change is only dependent on the parameters, not on the process. How does it go? Either it goes under constant pressure, or it goes under constant volume, or it goes under any other process. So it is basically dependent on the initial and the final condition only. And furthermore, delta U is basically dependent only on the temperature difference. And as we are dealing with the same condition in both the cases, that the temperature is going through the same change. That is, the delta T is same for both these processes. Either we go from constant pressure or by constant volume. So delta T remains same. So we can use this in the case of constant pressure as well. Okay. So this was for constant volume. For constant pressure, if we are dealing, what we can say is the work done dW is nothing but P into dV. So dW is nothing but integral of work is nothing but integral of dW, which is nothing but integral of P dV. That is P into integral of dV, V1 into V2. That is P into V2 minus V1. Okay. So basically, Now if we apply the first law of thermodynamics, that says that delta Q is equals to delta U plus work, and we know that delta U from the previous process, that is equal to NCV delta T. Now we know that at constant pressure the total amount of heat required is nothing but NCP delta T, which is derived by the unitary method only. So if we plug in all these values and the W can be plugged in from here, what we get is basically a relation between Cp, Cv and the work done. That is NCP delta T is equal to NCV delta T plus P into V2 minus V1. Okay. Or we can say that P into V2 minus V1 is nothing but NR delta T. So we can get that NCP delta T is nothing but NCV delta T plus NR delta T. And we can cut NR delta T on both sides. What we get is a very simple equation in terms of Cp and Cv and R. That is basically the relation equation in the specific heats of the gas, two important specific heats of a gas. Okay, now this is the first equation, or you can learn it in the different format, that is, let's divide both sides by Cv. So what we get is Cp upon Cv plus is equal to 1 plus R upon Cv. Correct? So basically you can get that this is gamma Cp upon Cv. So gamma minus 1 is nothing but R upon Cv. So we can get that Cv is equal to R upon gamma minus 1. So in terms of the ratio of Cp Cv, we can get basically the value for Cv. Okay. Similarly, if we have got that, we can get Cp. Cp is nothing but Cv plus R. So we get that R upon gamma minus 1 plus R. That is R into gamma upon gamma minus 1. So these are the basically two important properties of the gas, and we found the Cp and Cv in terms of the ratio, that is gamma and R. Okay. For monotonic gases, the very important, for monotonic gases, we have the property that gamma is nothing but 5/3. And how do we derive this is basically nothing but the internal energy per mole of a gas, monotonic gas, is given by 3/2 RT, because the degree of freedom are only 3 on it, and in every dimension kT by 2 is the energy distributed by the equipartition law. So we can say that Cv is basically 3/2 into R into T plus 1 minus 3/2 into R upon T. That is the change in the internal energy by changing the temperature by 1 degree Celsius. The temperature over here would have increased by 1. So if we subtract these two, we get Cv as 3/2 R. And using the relation equation, we can get that Cp is equal to Cv plus R, which is nothing but Cp is equal to 5/2 R. So the gamma gives us Cp upon Cv, which is nothing but 5/3. In a similar way, for diatomic gases, because they have 5 degrees of freedom, you will get Cv as 5R/2 and Cp as 7R/2, and you will get the gamma for the diatomic gas as 7/5. Okay. So basically in this lecture we did some very important concepts, like what is the first thermodynamical law, what is defined by the internal energy of a gas. Then we learned what are the various sign conventions related to the first law of thermodynamics. Then there was a very important concept about the internal energy, the specific heat of a gas, and what is basically meant by specific heat, and there can be infinitely many specific heats of a gas. Then we focused upon the basic two very important specific heats of a gas, that is Cp and Cv, and we defined what they mean basically, and using that information and the first law of thermodynamics, we derived a very important relation between Cp and Cv, that is Cp is equal to Cv plus R. Using that, we defined the gamma ratio for all of the monatomic diatomic gases, that is for monoatomic it is 3 upon 2R, 5 upon 3 the gamma, and for diatomic gases it is 7 by 5. So that's all for today. In the next lecture we will discuss some questions based on the concepts we have learned till now, and we will see various processes in the following lectures. First of all, in the next lecture we will discuss some questions based on PV graph as well as the concepts we have learned till now. Thank you.